Good afternoon. It's Ross Finlayson here in Seattle, Washington today, the January 13th, 2024. Gregorian. Well, today it's more of moment in motion, moment in motion, moment in motion, moment in motion. The idea, the concept of state and change is really reflective of Newton's laws. Rest is rest, motion is motion. But that's state, and there's change. So these are kinds of just usual parts of the reverie of what's available to anybody for thinking. And then our reflections and our culture and our canon really come down with a lot of background. Where here this is a general kind of consideration that there's a philosophical foreground. And then this philosophical foreground is a part of the philosophical background. And then it's kind of like, and as after the Buddhist and the aleya, the ground of things, which is basically a meditating person sits on the ground and finds in it kind of their fundament, our firmament, and that these are the kinds of aspects of the dialectic where then the thinking person can kind of reflect just on their own consciousness and mind, because it's a nice place to visit. So anyways, what I was going to do was read a little bit more from Waves and Layered Media, but I did want to take a look for a while at this quantum processes for the path integral, because I'd left off reading this and we never really got too far into it past what is kind of sort of the development of the formalization, the formalisms, the formulas of the path integral, and with regards to the line integral. And it talks about the Heisenberg picture and the Schrodinger picture. Coming is that the Heisenberg picture is as of the linear impulse arriving at a thing, that these waves and the particles and the particle wave duality are in as part of a wave train, or as of an aggregate, the flow of many of a multitude of waves. That these are the kinds of things then as go for the Heisenberg picture to the Schrodinger picture, where the idea of the Schrodinger picture is that at some point these waves collapse is the term, or as they coalesce, as they meet, or they form a moment that is a particle. This Schrodinger picture of the wave equation to, as it so collapses, any of what's the content of the moving linearly particle, its rotational and linear combined interactions is what makes a point or particle. So that's kind of the particle wave duality in the Heisenberg picture with Heisenberg uncertainty, and as we talked about here, Heisenberg certainty, and the Schrodinger picture and the Schrodinger's solution to the wave equation called psi, and as with regards to when and where, is as of various simple cases like the two-dimensional, and then what gets happening in the three-dimensional, and as with regards to degrees of freedom, and these kinds of things which reflect conditions of variation vis-a-vis the constant things. That then after that is all the new quantum physics since about 100 years ago. It's as following the old quantum physics, the electron physics and such, that are where it was known that the particle and wave-like things was discussed for hundreds and hundreds of years before the invention of electron physics and de Broglie firmly establishing that they're also waves. The old quantum mechanics is really just the extension of the old theory of atomism and the Democritan, and after Lavoisier and the notion that there are elements in the Democritan, and then as with regards to atomic physics and nuclear physics, molecular physics then resulting. So, and then he talks about the Dirichlet, and here one thing we talk about a lot is the Jordan measure is the line integral. So it's like, how long is a line? How long is a curve? Well, it's as of from an ant walking this line or curve, how long it takes given it has a constant velocity, or that's called Jordan measure, because for measure theory in mathematics formally today, to make it so like that, then it can't really be the same as the usual, what's called standard in the field theories, sigma algebras, measure theory, or measure 1.0. That measure 1.0 is a particular type of axiom addended to a theory of the complete order field that is after an axiom called least upper bound property, having that those are the two axioms added to descriptive subtheory to make it so that there's a complete ordered field. This Jordan measure then is not quite the same as these other notions of measure, because it kind of reflects as if a course of passage, infinitesimals in a row, or what here is called line rails. So there's Aristotle's continuum and line rails, iota-values, that only in all together and only in order and exactly so make a 0 to 1 line segment, a unit line segment. And then as for this Jordan measure basically defines that, so they renamed that a bit Jordan content, because they wouldn't want people to get the wrong idea that it was kind of conflating the notion in something that would actually also arise that is contradictory to it. So it's one of these really confusing things in the study of the mathematics, when the most familiar notion of a continuum is as of line drawing or constant motion. But the complete ordered field is only just like after that's all built, having fractions down on into it, which is where then you can define and follow derivations of delta epsilonics and get back down to zero and make, for the case of the limits of things, zero differences in the limit, the infinite limit. That there's lots that goes on into making for a finite theory everywhere, but as you get into the greater theory, then these things kind of come back to, assert their existence. And so anyways, yeah, Jordan measure can be properly called measure, and it's for all manners of mensuration and measure, and that's kind of the integral calculus. And so insofar as then the field reals have, after what's called the intermediate value theorem, the establishment of the fundamental theorems of calculus, the fundamental theorem of the derivative, and the fundamental theorem of the integral, which is computing the slope or computing the area, that these line reals, because they have a sigma algebra too, and they have least upper bound property too, then it results that they have the intermediate value too. So also the fundamental theorems of calculus will follow. They're both continuous domains. And then as with regards to why, it doesn't break the one to say that, you can't have points in a row, because then there would be a least iota non-zero quantity, because you can always take half of it or half of it or half of it again in the complete ordered field. That the complete ordered field and these line reals or Aristotle's continuum are two different things, and it instead is a result in function theory that this natural unit equivalency function, or sweep, between the natural integers and 0, 1 is not a Cartesian function. You can't reorder it. Whereas all other functions in this sort of theory, you can imagine the entire space of all the possible relations between the domain and the range, that they exist, in terms of there being a function so defined that way. That sweep is not a real function, but it's a continuum or infinite limit of real functions. In fact, the very most simple n over d for numerator over denominator. This is familiar to most people by now who have followed me at all. And it's been this way since about like 20 years ago, at least, when I said, hey, this is a real thing. And it took me a while to establish formally all the necessary rigorous formalisms why it is so. And now it is very strong. So anyways, then above the field continuity is this idea of the signal continuity. So the Dirichlet measure is that if you have a function that's, say it's 0 or 1, given that it's rational or irrational for the interval 0, 1. So on the interval between 0 and 1, or a and b, that it has a value either on or off for each of these values. Well, the idea is that in standard theory that the rationals are countable, so they have measure 0, even though they're dense and equidistributed and throughout this section of real numbers. And the irrationals, because they're the complement thereof, in the reals of the continuous domain as so modeled. That when you say real numbers, you mean a continuous domain or the linear continuum, or usually particularly the standard equivalence classes of sequences with the property that they are Cauchy. They have a limit, these sequences that arrive to all of them. That then this Dirichlet measure is either 1 or 0, and because it's either almost everywhere or almost nowhere a value of on or off. And then the idea that it's 1/2 is where these signal reals come in. It's a third type of continuous domain, and that's so established by anything that was twice the frequency of otherwise the fundamental frequency of things can do the perfect reconstruction of the signal, and so all analytical character is kept. In this manner, then, it's sort of a thing that mathematics doesn't really usually have a definition of a continuity, a continuous domain. It's got continuous functions in function theory, which is how everything is kept together. But it just uses laws of arithmetic after delta epsilonics usually, and these kinds of neat things. That how it so results is that there are these at least 3 continuous domains. Then that before the line reals, there's an integer continuum. This is an idea from like Duns Scotus, who was like a medieval monk in Scotland or something like that. Or Spinoza, who is a philosopher, he was a Sephardic philosopher in Spain. And the integer continuum then is that the integers go from 0 to including infinity. Duns Scotus was one of the first mathematicians who established with the approbation of the church that there was an infinite number, that infinity is in the numbers. And then Spinoza has it as so too. Somewhat later, Spinoza has it as so too, and it's a thing thusly in the canon that infinity is in the numbers, the integer continuum. So you kind of got this integer continuum, and then the ratio of 2 integer continuums makes up these line reals or Aristotle's continuum. Then for those, it just as they kind of fill out the numbers instead of filling in the numbers, it makes an ordered field of the rationals, and then it's kind of axiomatized and dropped in that, well, as the properties of a continuous domain, these would so follow. But because they don't have that first part, they just say that it's a given, it's a stipulation, it's an assumption, an assertion, it's an axiom. And then that for these signal reals on the far side, as being all the things that cross in the middle that could so make for that among them, they would fill it in. And it's funny because the line reals have a cardinal less than the cardinals of the complete ordered field. And the complete ordered field has a cardinal that's called C in the Aleph numbers of your Cantor and about countability and uncountability. And the signal reals kind of fall back in from what's called the long line of Emile de Bois-Reymond, who had this thing called the infinitar calcul, and where he was talking about infinite numbers and their ratios and stuff like that. So he considered all the expressions in real valued formulas and all the possible expressions. And there are more of those in the cardinals, but then they still come back down to this continuous domain. So this continuous domain, a linear continuum, still sits in the middle. That's how it is, briefly and quite fully, because each of these type of ways establishes their gaplessness, which is the property that makes completeness as a continuous domain. Then it's more of this repleteness. And then it makes for things that like a Dirichlet measure, and when it's 1/2 and not just truncated, 0 or 1, or the Jordan measure when it's not just renamed to something else for what it really is, that they're consistent together instead of being having some kind of problems of the hypocritical sort. Not enough critical. So, briefly. And so here the author, what we've been getting into was, it's after Gaussian and Eulerian analysis and the Wick rotation and keeping things Euclidean, and about the Wick rotation and its use of basically the the screw increment of Gaussian Eulerian analysis, or the complex numbers, facts of the complex numbers in the Argand plane or the Wessel plane, or otherwise for the complex numbers in their diagram and what they point to in the real number plane, r squared, say. This is kind of what we've been talking about. And so this is kind of in the definition of the sum-over-histories, which is kind of like the wave takes all the paths at once to arrive, yet still it's almost entirely just a straight line. This is kind of what we got into in reading this. And so this is kind of still in the preliminaries. And then as to where we had arrived at here, here I've kind of marked this as to where we got up to. So we got up to Euclidean action, the Jordan measure, the Riemann sum, the Lebesgue measure. The oscillatory nature of the exponential creates difficulties in including unruly paths, i.e. non-differentiable and discontinuous paths. So this is up into the Dirichlet and Poincare, and the Poincare rough plane, and the Dirichlet's notions of the continuous and discontinuous vis-a-vis the differentiable and not differentiable. That this was all late in the 1800s with Riemann and after Kronecker and stuff like that, but mostly Cauchy and Weierstrass, where Weierstrass first of all put his foot down and says, I got delta epsilonics figured out. My analysis is standard. And Cauchy was like, well, in these equivalence classes of these sequence of the ratios, they make a model of it, which they do. And so we call that Eudoxus Cauchy Dedekind, where Dedekind was a guy, and he kind of came up with, well, now we've said we've got this complete. And then he wants to get into some other uniqueness results, and this kind of stuff. But it's all basically based on Eudoxus, who's a Greek geometer about 2,000 years before them. But we say it's for Weierstrass that standard reals are well defined. And carrying on then we get into the Riemann sums, which are a really neat and easy metaphor, and they really mesh well with the idea of the sum of the differences, or Leibniz's calculus. And then what all they do is they kind of adapt to that while leaving behind a bit of what's called the raw differential, or treating it as an algebraic quantity by itself when it's infinitesimal, and so it couldn't really say that the indeterminate forms of those formulae and rigorously could really be said to kind of have a proper algebra. So in that sense, Riemann is famous for just kind of buttoning that up. And then some other aspects of Riemann's developments, because a lot of these mathematicians were interested in a bunch of these different things, is he got into like what would happen in as to regards to like discontinuities or whatever after the Euclidean and after geometry, that this Riemannian, or after Lobachevsky kind of first got into this with or without the parallel postulate among the postulates of geometry, the 4 or 5 postulates of points, then lines, then planes, then ... in geometry. Here there's instead a sort of quite Euclidean altogether geometry, but it's a geometry of points and spaces. So it just starts with points or spaces and just works in from that. And then the Euclidean geometry just kind of arises in the middle. It's very natural. Axiomless natural deduction, arriving at axiomless geometry. So, and then Lebesgue came after that and basically said, also we can do it in vertical instead of horizontal, and vice versa. One of the chief difficulties in constructing a rigorous measure for the continuum version of the path integral is the presence of the imaginary in its definition. The oscillatory nature of the exponential creates difficulties, including unruly paths. The exponentiated action tends toward a distribution. One of the greatest things about the exponential is because it's its own antiderivative, so it falls out or stays under in the addition formula for the operator calculus, just like powers and roots make for addition formula for the product space. The differential, when it's the exponential, has that it carries up and down its coefficients in the exponent and the coefficient. That's why it's so central in this kind of thing. It's not the only function, though, that is its own antiderivative. For example, this sweep function, this not a real function, yet quite standard and central and primary and continuum mechanics is an object of the mathematics, continuous domain. It's also its own antiderivative. So it reflects in our notions of the singularity theory and multiplicity theory that what was a uniqueness result is now instead a distinctness result. This is so because while the differentiable and continuous paths are everywhere dense in the set of all paths, it can be shown that taken alone they are inadequate to give a correct evaluation of the path integral. In point of fact, a careful analysis of the situation shows that these paths form a set of measure 0. Standardly, right? This situation is much like that of the real number line, where the set of all rational numbers can be shown to be a set of measure 0, even though they are everywhere dense in the real line. So you see, this author has exactly that to equip himself with a mental model of mathematics and a theoretical apparatus of a formula to arrive at these things. So simply equipping himself with this more replete definitions of continuity, I find one of the most compelling and beautiful things in mathematics. It's true, it's real, and it reinforces itself, and it's resistant to meddling. It's mathematics. Yeah, that's the nice thing about it. So we have an analysis and methods, and this sort of course is the standard way, and it stands up very well. So we get into Wick rotation, and we've read this part before underneath the talk about the reading from the path integral, that this is the same book that was being read in the path integral. Under the Wick rotation, form for the path integral, Dirichlet and and then we get the Euclidean action up in terms, the factors in the measure of the path integral become real under the Wick rotation, so the Dirichlet bar Q equals the limit, and this is the infinite limit, it's a line integral. It's Aristotle's continuum, a sort of summation. It's this time, has this time-ordered properties, or as whatever is a continuum ordered properties vis-a-vis the regularity of dispersion vis-a-vis the regularity of a fraction and ratio of the quantity m over 2 pi Planck bar epsilon t, that form of the quantity that maintains its relation of the dqi's, where epsilon tau is effectively d tau. The Euclidean action is identical in form to the integral of the Hamiltonian written in terms of q dot instead of p. And with this is regards to the Heisenberg and the Schrodinger sides of this thing, kind of like the outside and the inside of the gravitic singularity. A continuum boundary. The Wick rotation makes a mathematically meaningful measure possible. So we talked up about the interested readers recommended to the books by Rivers and by Glimm, G-L-I-M-M, and Jaffe, J-A-F-F-E. Talks about the continuous, the classical trajectory. Talks about the Dirac delta. Now the Dirac delta is another not a real function with real analytical character. It's 0 everywhere except at the origin, and then it's got an infinite spike with 0 width and infinitely high, with the added fact that the area under that spike equals exactly 1. The area under sweep also equals 1. And it's the only sort of discrete function that has an integral. It has quite a variety of interesting uniqueness results. Chapter 3, evaluating the path integral. So this is marked up. We've read this up into this a little bit. motion with a source. In this section, an evaluation will be given for the path integral describing the system of a one-dimensional point mass simultaneously moving in the potential VQ and undergoing an arbitrary external time-dependent force JT. The Lagrangian of the system is given by Lagrangian of q dot q equals 1/2 mq squared minus vq plus jtq. The function jt serves as a source for the particle's acceleration. As a result, jt is referred to as the source function. So that would be the force, and as we talked about here quite a bit, then there's the idea that there's the multipole, and so the notion also of that there's all the infinitely higher orders of acceleration and deceleration, and there's meeting and parting, and passing and the orbits of the orbifold, as all this stuff from the descriptive differential dynamics, and so on. Here it is the impetus which provides a propensity. And the Lagrangian is any sort of system defined as parameterized by time. So the Hamiltonian is a particular eigensystem approach that makes it possible to set up these quantum amplitudes and to solve for them in terms of linear superposition, then the eigensystems and the eigenvalues of the eigenstates, which preserve these vectors under these terms, which when they are added all up in a matrix, because we're dealing with 3 dimensions, and so it makes kind of a box of them. And then today, what they have instead of that, because they start anything that's nonlinear or has a skew or a bias at all, would make to introduce the Hamilton-Jacobi equations. And then that's all said to kind of fall under the Lagrangians, where that's basically would be like for Einstein's differential systems, eventually everything will have to be Lagrangian to be a differential system in Einstein's relativity. And then there's that... here we talk about the theory of some potentials, and that being as of up above the theory of harmonic functions, which is where the Laplacians, which is just that the second partials in all the different orthogonal dimensions are 0, has that that's what's called the theory of potentials, because it is the theory of those and all their relations, not just them, but all their relations. And then, as we talked about here, there's like this box corner Laplacian that is having analytical character outside of that. And so there's a fuller picture of that. The source function. The source function allows the definition of the generating functional, and this will be discussed later. It will be expeditious to begin with the simpler case of VQ equals 0 and return to the case of a non-zero potential afterward. The method of evaluating the path integral will be an application of the discrete method to the form equivalent to 2.47. The appropriate Lagrangian density is given by Lagrangian of P comma Q. So instead of Q dot Q in the Heisenberg or the Schrodinger, then it's P comma Q in the Heisenberg and Schroedinger, equals PQ dot minus P squared over 2m plus JTQ. As to regards, because VQ equals 0. And so that this 1/2 MQ squared and this PQ dot minus P squared over 2m allowed the replacement of the one for the other, of the Heisenberg into the Schrodinger picture, or vice versa, as follows that from its singular, and so that's where they meet, and it's indeterminate form, that they're a determinate form. This is how these things fit together. The measure 2.46 derived for this form in section 2.2 is appropriate since the particle's motion can range over all phase space. Here, as we've been talking about only even recently in the wave functions and the phase space and the amplitudes and the modulation. These are aspects of the spectrum analysis, and what with regards to is the the static rotational moments in otherwise linear things. This is all the spin in otherwise the fall or the draw or the line. It's one thing. The transition element is given by the path integral, the z of the QATB, QBTB. So on the left and right for the amplitude and the time from A to B is the integral from QA to QB of the DQIs of the DPIs over 2 pi Planck times e to the, and then this quantity I over Planck, and the sum of the from j equals 0 to n minus 1 or infinity of the p sub j times q sub j plus 1 minus q sub j are the incremental differences. And as regards usually in a straight line that's 0 or a constant, or they just add up to 1, line integral. Minus epsilon over p squared sub j, p sub j squared rather, over 2m, plus epsilon j, the source function, t sub j, q sub j. Rather than integrating the p sub j variables to create a path integral that is Gaussian in the qj, it is simpler to perform the q sub j integrations first. The result is a product of infinity minus 1 Dirac deltas, reducing the path integral to z of the QATA QBTB equals 1 over 2 pi Planck. This integral of the in the DPIs. So in infinitely many of these, they get integrated all as together, they're products. And then the Dirac delta basically says it's only 1 in this for each product in its own spot. So it's kind of like summing all together all these products as if drawing a line right out through all these dimensions that's only filled in on the line that is holding it out in this scaffolding and this tenting in the space in this way. So it's kind of like the identity dimension in that way. It's one of those graphical elements that happens to also be the mathematical element. The result is a product of infinity Dirac deltas, reducing the path integral to this dot dot dot. Where we left off was of those times the Dirac delta of this epsilon source t naught plus, where naught is the first thing. T sub 0 just means time at 0. J of t naught plus p naught minus p1, or the first two elements of this way. Dot 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 of the Dirac delta of the epsilon j of the t, infinity minus 1 of the p of infinity minus 1 minus p of infinity minus 2, or the last, from the first to the last. Times this e to the, times the quantity I to the Planck of this p sub n minus 1 q sub b minus p naught q sub a, or the endpoint conditions, their difference, plus epsilon source t naught qa times e to this quantity negative I epsilon over 2 m Planck times the sum of j equals 0 to infinity minus 1 of the p sub j's squared. So that I'll have to look at it into. I would look into that and start trying to draw out its construction. And it's got this product of the two exponents, so they have an addition formula. So whatever is this product, it also happens to be those two things just added together. And so there's some ways to think about how to set that up with a brief rewriting. Now he says, the first infinity minus 1 integrations are now trivial to perform. The resulting form for the path integral becomes equivalent to the single integral. This is the z of the QATA QBTB. equals this long expression called e to the I over Planck q sub a and times the sum of all the source functions for the times segments times the integral of the integral in each of the segments, each of these infinitesimal segments. So the way he's written this integral is to make a summas over these infinitesimals. So it is kind of like the line integral, or adding up the iota values. And it's remarkable that the real function sweep also has a doubling space. It's a thing that the signal reals coming back in kind of have a halving space because it takes twice as many to make a perfect reconstruction. Whereas the line reals have their one-sided or two-sided points, and so and as to so regards that they're put into one-sided points, then it has a doubling space. Or the revitalization of measure theory after a guy named Vitali, for whom all this notions of measure theory first became after Weierstrass so relevant. So Weierstrass and Vitali together go a long way towards defining analysis, the integral calculus, real numbers in the integral calculus. So that is still in the middle of that function. Then the next piece of it is, again, this I over Planck, and then that reflects just being part of this whole Gaussian analysis and about the analyticity and the screw interval, screw increment as it's called, and then the also the reflections and rotations as after back down from Wick rotation. Minus I over Planck, or that being the P of n minus 1, or the endpoint minus QB minus QA, minus this I over Planck, sum 0 to infinity minus 1, epsilon over 2m of the endpoint minus the sum from k equals j plus 1 to infinity of the epsilon source tks, or each of those squared. So the squaring, it makes up for this addition formula and exponents that's like a doubling space in the addition formula. Expression 3.18 is actually simpler when the continuum limit is taken. Denoting the integral over the j sub t as the impulse I sub t. So big I is written often for moment and also here for the impulse. Equals, or it's on the order of the integral from t to t sub b of the dt in the dt's, or integral over those differentials, source tau, or it's in d tau source tau, equals the integral from ta to tb, or the integral in time from beginning to end, of d tau and d tau of theta tau minus t source tau, and writing p infinity equals p in the limit epsilon goes to 0. It's integration as of by iota values, or by methods of exhaustion, and in the limit, the continuum limit, the path integral becomes that z qa ta qb tb equals e to the I over Planck qa I ta times integral from negative infinity to infinity in dp of 1 over 2 pi Planck e to the this quantity altogether I over Planck p times this quantity qb minus qa, or the difference from beginning to end to beginning, minus I over Planck. Anytime you hear that, you just reflect that it's stacked up about this Gaussian unilarian analysis back into the Wick rotation, so that it's under this line integral going through the integration of all these quantum amplitudes as after those to make an overall classical impulse, sum-of-histories, the integral over the time of p squared over 2m minus p over m I sub t, or I of t, plus 1 over 2m I squared t. And then that reflects kind of one of these, it's I squared minus I, all that over m, and gets back into kind of a negative x squared plus minus 1. So a lot of these concepts in the geometric and the methods really kind of keep finding themselves again, because quadrature is really great for keeping the measure in terms of right angles and straight lines. It's the diagonal. And he goes, now we've read some of this before, I'm pretty sure, but I did want to kind of get back up to pace where we were at in the reading from the path integral, and having learned some other things about what's relevant, both from reading from Einstein and the whole descriptive differential dynamics bit, and moment in motion. So I'm going to leave off from that for right now, but we get to talking about the transition element between two instantaneous momentum eigenstates, only if the classical impulse relation is met. This functional has the important property that its functional derivatives give the matrix elements of products of the Heisenberg picture operator big Q's of t between the two instantaneous eigenstates. And then he has this exercise 3.4 again. Show that negative I Planck of delta of the ZABs of bracket J of the delta JTs, so where they coincide, so that the Dirac delta is basically a filter, and it says only where they meet is at 1, and everywhere else is 0. So when you take their product together, you don't have to worry about them anywhere else having any product left over or residue. It's just right there where they line up. So in this case, the Dirac deltas are just kind of saying it's like that's our windowed box, and this kind of stuff. Ends up equivalent bra of QB-TB of the QT, the Heisenberg picture operator, QATA, subscript J, where the subscript J serves as a reminder that the propagator is to be calculated for non-vanishing source, because as was mentioned, when it's 0, it kind of has singularity, and so there's a form for it. And so this is as with regards to and as to where in the scattering and tunneling of these particles that they got their tendencies and propensities and are moving by least action or action. This is the formula that it has from that. From this exercise, it should be apparent that expectation values of Qt for the free sourceless theory discussed in the previous section can be obtained by simply evaluating the functional derivatives of Jt equals 0. So what he said. Using the result that delta I t prime over delta Jt equals theta t minus t prime. So this would be after angle approximation, I think. I'm not quite sure how to read that. And the functional chain rule expectation value of Qt is given by Q8 bra of Q8TB of this Qt, or conditionally and into Qt, the probability amplitudes, Bayesian, of Q8TA, subscript J equals 0, equals negative I Planck of the deltas ZAB of J, delta JT, evaluated at J equals 0, equals this quantity QA plus this quantity QB minus QA over TB minus TA, which looks familiar as from this sort's diffraction settings, differences of fractions, diffraction, times this quantity T minus TA, all that times ZAB of 0. Therefore, the nth order functional derivative yields the time-ordered product of n factors of Qt. So he's kind of made his point then that that's what he's set out to establish as so. And it's kind of a linear function there of this entire system of all these coordinates and the actions and this and that and the time. 3 space dimensions in 1 ray of time. So that's pretty good. Now I think this is about up to where we've got in reading the this book. So what I thought to do was then just skimming a bit. I'm just curious. He says the concept of the generating functional was first introduced by Werner Heisenberg and H. Euler. So I wonder if this is like a descendant of Euler or something. In Z Physik 98 in 1936, the modern formulation stems primarily from the work of Schwinger, 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 C.J. Schwinger, Proceedings of the National Academy of Sciences, USA, 1951. J. Schwinger, Phys Rev 82, 1951. J. Schwinger, Particles and Sources, Gordon and Breach, New York, 1969. See also K. Szymanczyk in Z. Naturforschung, 1954. Feynman and A.R. Hibbs, Quantum Mechanics and Path Integrals, McGraw-Hill, 1965. So Feynman is quite famous for the path integral, which he learned from these people. This definition is adapted from G. Jonah Lacinio, 1964. So I'm not sure if that's a particular reference in the text. This is reference for this whole chapter. And then Zumino in Lectures on Elementary Particles and Quantum Field Theory, 1970, Brandeis University. L. Schiff, Quantum Mechanics, 3rd edition, McGraw-Hill, 1968. Schulman, Phys Rev, 1968. Iguchi, Gilkey, and Hansen, 1980. Nash and Sen, Topology and Geometry for Physicists, Academic Press, 1983. Nakahara, Geometry, Topology, and Physics, 1990. Karo, Fari, and Gutmann, 1990. Phys Rev D, 42,1194. So then he says, in getting in chapter 4, and now we're not so much reading along and reading this for quite following the entire derivation, but I just want to look and see what it says about things. Harmonic oscillator. See, now, harmonic oscillator is something we looked into a bit in the descriptive differential dynamics and the wave theory. And it deserves quite a deal because it represents a lot of what goes on in terms of the oscillating and the restitutive, vis-a-vis the attenuating and the dissipative, those being these things that when things stay together or go apart. Either how they do or that they do. It's that descriptively, those few terms kind of reflect that in anything that does, it's like it does and how it does. Or it does and is doing. These are two different things on either side of the temporal modality, since when or when it will, these things. In that sense, it's kind of a fair expansion of, otherwise, the principles of the least kind of thing, because the least isn't necessarily sufficient. But not much more is needed, and any much more is underdefined or overdefined. So it's about trying to find that balance of the things that end up being judicious and having a paucity to them, efficient, insufficient. Natural units. Quantum mechanical and quantum field theory calculations can be rife with the powers of Planck's constant. And then Planck's constant is written little h, or it's written little h with a little strike through it, or bar, and so it's called h. It's called Planck, and so when I say Planck, I usually mean h bar, which is Planck's constant divided by 2 pi. It equals 1.05 times 10 to the negative 27. So 27 zeros, 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 27 zeros, 105 erg seconds. And the speed of light, c, equals 2.99 times 10 to the 10 centimeters per second, usually 2.98 times 10 to the 8 meters per second. So this is where in the empirical units, sometimes besides the standard units, where the standard units are the units, they don't have like the centi or the prefixes that reflect the coefficients on them in the decimal coefficients, where of course everybody should know that all these types of standard units have their coefficients to define their powers of 10 higher and their powers of 10 lower. So centimeters is just 1/100th, or 110 squared, 1/100th meters. And so when you have grams, meters, and seconds is different than centimeters, grams, seconds, because sometimes by using those units instead and those constants instead, they mean an entirely different empirical interpretation. And so when you talk about, and I don't know so much about them, but like MKS, meters, kilometers, and seconds, or these kinds of things, or meters, kilograms, and seconds, are different than meters, grams, and seconds, MGS. So where the author just writes this like, here's the constant, you're like, well, yeah, I can get that from the table, it's the same everywhere, and he puts it in the units, he might mean something like that. The manipulations can be greatly simplified in appearance by using natural units, in which H and C are set to unity. So the natural units is a great thing because all the formulas that then you use after that, you set it up so that really I'm only going to be doing something that's different from that as like either 0 or infinity. So by setting that to 1, then in all these other formulas where that's like a large number or a small number, you instead carefully use formulas like for the differential geometry, where it's like, we don't have anything that's infinite or 0. But in the middle, some things are kind of closed forms. So it's simple with natural units, it's similar. And so at the same time, and when you have a theory that like, well, something happens faster than light speed in the theory, but everything that's the maximum. So natural units are great as long as they apply. In statistics, you'll find a very similar thing called normalization and standardization. You divide out the size parameters until it equals between 0 and 1, or between -1 and 1. Standardization and normalization. It's almost kind of similar in discretization at all, and what's called the normalization of particle values is being fixed and being particles, after we've been just talking about running constants and the conceit of particle wave duality and points and particles. Keeping things normal. Yeah. So normalization is after denormalization, and natural units are veiled in a sense. For example, as a result, in natural units, all physical quantities may be measured in powers of only one of these fundamental units, or any one of the units derived from them, such as energy. For example, a typical mass appearing in formulas is that of the electron, where mass m sub e, or mass of the electron, equals 9.1 times 10 to the negative 28 gram in the SI system. He wrote grams as GM, where I'd just rather see it as G, because giga would be capitalized, and whereas though it's possible that it wouldn't want to be read as a variable in terms of that. But in the natural units, m sub e may be measured in electron volts. M sub e equals m sub e times c squared equals 8.19 times 10 to the negative 7 erg equals 0.501 mega electron volts. Inverse length m sub e equals m sub e times c, or Planck, equals 2.59 times 10 to the 10 inverse centimeters, or inverse time mass of the electron equals m sub e c squared over Planck equals 7.75 times 10 to the 20 inverse seconds. Conversely, the appearance of 1 over m sub e in a formula may represent a time or a length. So this goes back to the idea that in electron physics and for energy, It's the whole idea of how electron physics founds the old quantum physics. It's exactly the kind of the sort of the reason why then when it gets up into these higher empirical realms, that having it in these natural units is great because it allows you to kind of treat things all together with the same set of formulas. But what it doesn't do is, and then detail in the deconstructive account that what results so necessary for these different kinds of radiation, what they mean and how they are to be. So it's something to be said and understood that the discretization that resulted for electron physics, a theory after Hooke and Clausius, and after Kelvin, and after Rayleigh and Jeans, and then for Millikan and Young, and the electron physics, and that the typical mass in the formulas is the mass of an electron. And it's Feynman's favorite milieu because then you can treat everything like an electron. It's just to be understood that energy is kind of a universal medium of quantity, but it's attached to its further description and thus must be disambiguated as necessary. So that just speaks really a lot to the previous talk about electron physics, and then as we get up above kind of to the neutrino physics, or for the ultraviolet catastrophe, which led to electron physics, to the infrared catastrophe, which leads to neutrino physics. Then it gets kind of better again because it includes this continuous, it includes this infinite again, normalized. Well, all right, that's about a reading for today. We skipped ahead a little bit in this book, there's so much more to be read because that's kind of like where we left off in reading from the path integral, reading the path integral. Well, let's see then. Have a great day. I shall so hope. You know, it's cool and chill, and see the little band here. I'll wind it up, and it's just an apparatus of clock springs and clockworks and after material properties that it keeps time, right? And boy, it sure is hard these days to find a couple different things. One is a sundial, and the other is a old scaled gradiated mercury or alcohol thermometer. Well, because the sundials didn't, right, and the thermometers they've kind of dialed it down. And then as we were talking about last time about -40 or 40 below, that's the same in Celsius and Fahrenheit. And when it comes to interpreting temperatures, I don't really understand Celsius very intuitively because it's a little bit too close together to tell the difference, where in Fahrenheit, 5 degrees makes kind of a difference, but in Celsius it's only like 1 or 2 degrees. But from what I understand is that 30 Celsius is about 100 degrees or too hot for humans that don't necessarily have thermal control, for mammals that are warm-blooded. And 40 degrees is Death Valley, which used to be the hottest recorded temperatures on Earth. Hey, well, with that bit of grim reminder, have a great day. Stay cool.